Chapter 2 Towards the Modern Atomic Model 2 Chapter 2.1 Atomic Spectra and Bohr's Model. Let's begin. Different colors of flame. If you study chemistry, you must know flame test. Metal sources on fire give out different colors of light depending on the metal and iron. Why is it so? Light is given out due to electron transition from higher to lower energy levels inside an atom. By studying the light given out, we may study the energy levels structure of an atom. 1. Light spectrum. Using a plane transmission grating, we may see the light spectrum produced by a gas discharge tube. On the other hand, the spectrum produced by a filament lamp or that by the sun is a continuous spectrum. Let's take a look at the experiment 2A, emission spectrum produced by discharge tube.
All objects emit electromagnetic radiation. We can use a plane transmission grating to study the spectrum of radiation. Look at the hydrogen discharge tube through a fine grating from a distance of about 1 meter. We can observe some bright-coloured lines. This spectrum is called the emission spectrum of hydrogen. Now, replace the hydrogen discharge tube with a mercury discharge tube. Look at the tube through the grating again. Observe the spectrum obtained. Compare this spectrum with the one obtained before. Are they the same?
Lines of different colors are observed when the emitted light passes through the grating. It is an emission spectrum, and it is a light emission spectrum or emission light spectrum. The lines of different colors shows that gas discharge tube produces light of certain characteristic frequency only, but not a continuous range of frequency like a filament lamp. Moreover, different elements have their own characteristic emission spectra. B. Absorption spectrum. A filament lamp produces a continuous spectrum, which consists of a continuous range of frequency of visible light. If we observe a continuous spectrum using a transmission grating with low-density gas in between, the low-density gas will absorb certain frequencies of the light. The result will be an absorption spectrum. Let's watch the following video to see what absorption spectrum looks like.
In this experiment, we will observe the absorption spectrum of iodine vapor. First, look at the filament of the ray box through a fine grating from a distance of about 3 meters. We observe a continuous spectrum. We now put some iodine crystals into a large boiling tube. Cork the tube lightly and heat it with a Bunsen burner. Warm the test tube until the iodine vaporizes and deeply colors the tube. Now, place the tube in front of the ray box and view the filament of the ray box with the transmission grating. We get another spectrum. Compare the absorption spectrum with the continuous spectrum obtained before. What can you observe? The second spectrum contains some darker lines. called absorption lines. This spectrum is called an absorption spectrum.
So, such a spectrum with a continuous colored background but darkened lines is called an absorption line spectrum. This is the result of photoabsorption, followed by irradiation of light by the low-density gas before the light reaching the observer. Scientists compared the lines in the emission spectrum with those in the absorption spectrum of the same element. They find that the wavelengths of those lines are exactly the same. We now know very well those lines are due to the electron transitions inside the atoms of the element. So light spectra are just fingerprints of elements. They are related to the energy levels inside an atom. Different elements have different sets of light spectra. When atoms are excited by electricity, electrons are promoted to higher energy levels. EM wave is produced when excited electron returns to lower energy levels. Many electrons demole from higher to lower energy levels. These electron transitions together produce an emission spectrum. On the other hand, when an electron absorbs a photon of certain frequency, it is promoted to higher energy level. When an excited electron returns to a lower energy level, the absorbed photon will be emitted to any direction. The intensity of light of that particular frequency becomes lower in the forward direction, and therefore that particular frequency of light appears darkened in the spectrum. This produces an absorption light spectrum. Example 1. Analyzing the composition of elements. As the light spectra are just fingerprints of elements, we may compare the samples A and B with the known spectra to identify the elements exist in the sample. It is also the method used by astronomers and scientists to identify the compositions of a distant star. C. Evidence of the energy levels of atoms. According to photon model, frequency of a photon determines its energy. So light spectra suggest that atoms of the same element allow electron transitions between certain energy levels only. In other words, the energy levels of an atom are specific, but not arbitrary. And now we know that they allow the orbits for electron to perform circular motions must satisfy certain conditions. Do check point 1 below.